Okay, hello, period 4. I'm making a quick 10-minute video for you now. There was one thing that we did not get to in class because we only had a half an hour class yesterday, and that was this very important problem. This is problem number 109. Problem number 109 said there is this position function, x of t. In other words, this is a function which takes as input a time and outputs a position along the x-axis. And this is just one of these rectilinear motion problems, motion in one direction along a line. And specifically on the time interval 0, 5, and the question was, find the total distance traveled. This is an important problem, I think, which connects together several of the big strands of this course from the past month. In some ways, everything I'm about to do is sort of obvious, but this is, again, sort of bringing it all together, and this is the kind of problem you can do immediately after doing the fundamental theorem of calculus, and in some ways helps explain the fundamental theorem of calculus. So let's go. First of all, if I'm being given the position function, and I'm asked for the total distance traveled, the first thing you might think is, dude, is this just easy? Because I can tell exactly where I am at any given time. So, for example, what is x of 0? Well, if you plug in 0, you get -2, which means, if I were to draw this number line here, it means that, okay, here's 0, and at time 0, I'm here at this point -2 at t equals 0. And, well, what is x of 5? My position at time 5. For this, possibly the fastest way to do this is using synthetic substitutions. So, okay, just very quickly, I get 18, and I think that that is right. So that tells me that I will be way out here at 18 at time t equals 5. So if you don't think about this too much, you might think, oh, I started at time 0 at position -2, I ended at time 5 at position 18, therefore the distance traveled is 20. But that would be wrong. What we do know, because and the reason why it's wrong is, we don't know exactly what happened to this function in between time 0 and time 5. If the object was moving completely to the right the entire time interval, then indeed the distance traveled would have been 18. But we don't know that for sure. It's possible that if the object was moving both left and right and back and forth, then the distance traveled could be greater. So what we do know, this x of 5 minus x of 0, which we just calculated to be 18 minus -2 equals 20, this is the displacement on the interval 0, 5. And displacement is just a synonym for the change in position on this interval. Okay, and so we do not use these terms casually, distance for displacement. Displacement means displacement. It's just literally like how far you are away from where you started, but the distance traveled is measuring something else, and that is what we want to know. Okay, so how can we answer this question? Well, if we're given the position function, then one thing we could do is just differentiate. So if we take the derivative of x, then what we get is 3t squared minus 12t plus 9. And now this is like back to stuff that we did like a month ago. I now have a velocity function. The derivative of position is velocity by definition. And if I factor out a 3, I get t squared minus 4t plus 3, which means that my position function is actually 3t minus 1, t minus 3. Well, using our knowledge of the relationship between a function and its derivative, I can tell you, well, first I can just make a sign chart for velocity. And the sign chart, well, I won't go from -infinity to infinity because I only care about the time interval from 0 to 5. But even on that interval, I see that at 1 and 3 we change direction. And the sign chart is quadratic-y, so it's a quadratic, so it's plus minus plus. Aha! Now I know that on the time interval 0, 1, I'm moving to the right. On the time interval 1, 3, I'm moving to the left, and on the time interval 3, 5, I'm again moving to the right. Therefore, since I do backtrack, my distance traveled will be greater than 20. And the one way to finish off this problem, to find the total distance traveled, doesn't require integrals at all. Since I have the position function, I can just calculate the distance traveled on the interval 0, 1. And here, since I'm moving right the entire time, then on that interval, my distance equals my displacement. And so what is x of 1 minus x of 0? Well, perhaps it's worth it to scoot back over here and find my position at time 1. It's going to be, yeah, okay, let's just do it. Boom, boom. It's 2. Okay, so x of 1 minus x of 0 is my position at time 1 minus my position at time 0, which is negative 2, so 4. Okay, so I traveled the distance of 4 on the interval from 0 to 1. Okay, how about the distance traveled on the interval 1, 3? Well, if I do x of 3 minus x of 1, calculating the displacement on the interval 1, 3, I expect this displacement to be negative because I know I'm moving to the left. So again, we calculate it, I find out what's happening at 3, negative 6, 9, negative 2. So that's 3, negative 3, negative 9, something went wrong. What the hell am I doing? 1, 3, negative 3, negative 9, 0, 6. Maybe I didn't do anything wrong. It's 4. Sure. No. What the hell happened? My position at time 3 is 1, 6, 9, 2, 1. Yeah, I guess it's just 4. I somehow remember it being something else. Oh, yeah, because I messed up. That's 0, that's negative 2. Okay, so my position is negative 2. So at time 3, I'm at negative 2. Of course, I need to be farther back at time 3 than where I started at time 1. Time 1, I'm at 2. And so the position at time 3, which is negative 2, minus the position at time 1, which is 2, gives me negative 4. Okay, well, and actually, well, whatever. Negative 4, all right, and finally, what is my position at time 5 minus my position at time 3? Well, my position at time 5 was 18, and my position at time 3, I just calculated, was negative 2. So on this interval, I moved forward by 20. And so, okay, here it is. I traveled 4 to the right on the interval 0, 1. I traveled 4 to the left on the interval 1, 3. And I traveled 20 to the right on the interval 3, 5. Thus, my total distance traveled is 18. And that is the answer to this problem. Okay, so why are we still even talking about this problem? And what does this problem have to do with integration? And why were they giving some strange directions of what to do in this problem? Well, that's because this is a pretty atypical problem. Being given a position function and then being asked sort of information about the displacement. What would be more typical is if we were given a velocity function and asked to analyze it. And in fact, to know the total distance traveled on this interval, I sort of don't need this much information. In particular, this negative 2 is kind of irrelevant to me because actually what position I am at on the number line shouldn't matter if all I care about is the distance traveled on a particular interval. And so what would be more typical would be to just be given a velocity function and to be told that it's 3t squared minus 12t plus 9. And then, based on this velocity function, to be asked, what is the distance that an object following this velocity function travels on the interval 0, 5. And intuitively, it is sufficient to answer this question, how much distance got traveled, if given just this velocity function. Okay, so let's go. Well, I've already factored this as 3t minus 1, t minus 3. And now perhaps what we can do is make a visual representation of this velocity function. So that's what I'm going to do now. So here is a picture. Okay, I've done this already, but when you plug in 0 into this function, you get back 9. At 1 and at 3, we have roots. So here's 0, here's 0. When I plug 5 in here, I get 2 times 4 times 3. So that's 24. Okay, so picture not totally to scale. What we have here is a sketch of velocity versus time, and it's going to be parabolic, right? It's going to look something like that. Okay, so what I'm now doing is I'm bringing integration into this. Here I have a velocity function, and I want to know how much distance traveled. Well, we can sort of break this up into 3 different kind of pieces. What if I just look at the area here? Well, this is the integral from 0 to 1 of the velocity, and as we've been talking about, the integral from 0 to 1 of the velocity function is just going to be the distance traveled over that interval, and here we know that this is 4, because we've seen it already. Okay, and then over here, I have another sort of area that I'm interested in. Well, if I just take the integral from 1 to 3 of the velocity function, this is going to give me negative 4. And the absolute value of that is the distance traveled on the interval 1, 3. And finally, if I go here, and I take the integral from 3 to 5 of velocity, that is going to give me 20. And so what we have here is a visual representation of exactly what's going on. And in fact, this goes back to the whole reason why we defined integration the way we did in the first place. We wanted, when you take the integral of a negative function, for it to count negatively for this very purpose. That when we take the integral of a velocity function from 0 to 5, if I were given this velocity function and asked for this integral, the answer to this is going to be 20. Because this counts positively, this counts negatively, and this counts positively. So we want them all to and this is the displacement. But if I want the distance traveled, then what might we do? Well, our book says to do the following, to take the derivative of the position function, which is velocity, and then to take the absolute value of it. What is the absolute value of velocity? Oh, we have a word for that. It is speed. And I'll now make a picture of the speed function. What does the speed function look like? It looks like this. And now you see that the area under this speed function is just going to sort of make all of these things positive. And now we're going to have 4 plus 4 plus 20, picture not to scale. And so what the book actually tells you to do is to take the derivative, take the absolute value of it, and then take the integral from 0 to 5 of this. And that, it says, is going to give you the total distance traveled. Okay, so these are like basic connections of all the things that we've learned this semester. The integral of a velocity function is the displacement, but the integral of a speed function is the distance traveled. And the final thing, because the book did just sort of say without any explanation, it said to just like do this. If you were doing this by hand, what would you actually do if someone told you, just sort of out of the blue, to take the integral from 0 to 5 of the absolute value of 3t minus 1 t minus 3? Well, the only way to actually do this integral of an absolute value is the way we always treat absolute values in all of calculus and mathematics, is to break it up into casework. Presented with this integral, what you would do is figure out on what intervals it's positive and negative and split it up into 3 different intervals. And so there's no shortcut to doing this except using a calculator. If you were doing this, you would make a picture as we have done, and then you would say, okay, we're going to take the integral from 0 to 1 of the velocity, expecting something positive because velocity is positive, and then we're going to subtract the integral from 1 to 3 because we know that the velocity is negative on the interval from 1 to 3, but we want the positive of it. And then we add the integral from 3 to 5. So presented with the problem and being asked to do it by hand of calculating the distance traveled, we just do 3 separate integrals and add them up. And the final thing I'll note is that were you to actually do this integral, you would now apply the fundamental theorem of calculus, which is to say, take an antiderivative of velocity. And the antiderivative of velocity is position, sort of. And so what you would get is basically x of 1 minus x of 0, which is exactly what we got when we did this problem 5 minutes ago the non-integral way. minus x of 3 minus x of 1 plus x of 5 minus x of 3. And these x's that I'm just mentioning here are not actually necessarily the position function that I was given at the beginning of this problem. What it is, in fact, is just an antiderivative of velocity. So you could use the position function given in the beginning of this problem, or you could use any function whatsoever, which is an antiderivative of velocity, which will differ from our position function by a constant. But those constants are going to cancel out, and that's sort of another sort of explanation of why the fundamental theorem of calculus makes sense, because it doesn't matter what position function you use, it doesn't matter what antiderivative you use, they're all going to be the same. Good, that's all.